about Poisson process has three important properties. First is the number of points in the interview T1, T2, with length T equal to T2 minus T1. It is a Poisson random variable with parameter lambda t. So it means the number in the time interview T1 T2 equal to k. Probability is equal to e power to 2 minus lambda t and k over lambda t power k over k. So this is his probability masses. And the second properties is if T1, T2, if two time interval has no overlapping area, so the random variable, the number in the random variable in T1, T2, or T3, T4 are independent. It means that they won't influence others random variable in the time interval that are not overlapping. The third property is using the point Ti, we form the stochastic process xt equal to 0 to t. So also we can easily get use we can assume lambda t equal to alpha, and we can use we can get the sum of all the points since the probability we know every point, we can consider it as every point k equal to 0, 1, 2 to infinity. So we can get the sum of this probability, and then we can get the mean is lambda t, and also we can get the autocorrelation and the autocovariance. About Poisson increments, it's a bridge to connect to transfer to the Poisson impulse, and it's defined as in the time interview epsilon and xt plus epsilon minus xt, where xt is the Poisson process we mentioned before, and so we can get that the probability mass and the mean of the yt. Here we use yt to present the Poisson increments, and since it stands in the time interview epsilon, the point, the increased point rate, the rate of the increased point. So it's not a function about t, since here we divided epsilon is t here. So we can get the mean is lambda, and the autocorrelation we can get and the autocovariance. About Poisson impulse, we define a stochastic process zt as follows: zt equal to the differential xt about t of t. So it's also can be considered as the epsilon it goes to t0 and the value of yt. So we can get the probability mass. Here is no definition about probability masses, and we can get the mean is also lambda, since it's about it's a transfer, it's other form of yt. So we also can get the autocorrelation and autocovariance. About the semi-random telegraph signal, we define a stochastic process is defined as xt equal to 1 k z1 k. It means that the number in the interval to 0 to t from 0 to t, the number of points is even, so we get xt is equal to 1, and we get xt equal to -1 where k is odd. We can get the probability masses. Here are only two situations. One is equal to 1 and one is equal to -1. And we can get the probability masses. And we also can get the mean and the other covariancy. We can see that the covariancy here is about it's a function about t1 minus t2. So, and the mean here is the mean here is not a constant, even though the correlation is a function about tau. So, Poisson impulse is not a WSS. And the random telephone signal, semi-random telephone signal here, we need to know that when t is 0, it means that k must be 0. K must be 0, so x0 must be 1. So here is not a random variable when x0. So it's not totally random for xt. So we define x0 when we define this stochastic process. So we need to define a totally random telephone. We need to define a totally random telegraph signal. We need to add a random variable alpha, where alpha, when alpha is alpha equal to 1, or alpha only has two value, and one is 1 or other is -1, the probability are equal to 1/2. So we can for new process yt equal to alpha xt. So now, even though we know x0 here is 1, but we cannot know y0. So you see here is another variable alpha. So we can get the probability masses and the mean and the correlation and the covariancy. About the random work, random work is defined as a tossing of a fair coin infinity times. We define x and t equal to ks minus n minus ks. Here k, we need to know k is the number of the head, and n minus k is the number of toy. So we use the difference of the head's number and tail's number. We define the new process as x and t, and where we also can write it as xt, where t is bigger than nt and smaller than n minus n plus 1t. So we also can get the probability masses. It's not very hard, and we can find the mean as the correlation or covariancy. So in random work, it's a stochastic process. It consists of random variable. We can consider it as a random variable which consists of many independent random variable yi. We can introduce a random variable yi and it defined as yi equal to s or minus s. Since when we tossing, we only can get two results. One is head, one is toilet. So head means we get a positive s. But when we get a tail, we define it as we get some minus s. So here x and t is the sum of this yi, where I is 0, 1, 2, 3 to goes to infinity. So it's a sum of this result. But we need to know here yi is the independent tossing process. So we can get the sum of yi get the sum of yi, and we can get the mean of xt. And we also can use this method to get the autocorrelation or the autocovariance. Okay, move to the Wiener process. We define Wiener process as a limited process of random walk where the t goes to 0, s goes to 0, and the total time goes to infinity. We need to know Wiener process is a little special here, and Wiener it's a limiting process of random walk. Is distribution function is here. This distribution function is density function is a form of Gaussian white noise. Is a normal distribution. Its density function is a Gaussian function, and so it goes back to the Wiener process. We can get the mean. Its mean is 0, and the autocorrelation is here. So here we need to use the normal distribution properties to get its first order density function, the distribution function. Okay, that's all.